I'm going to go over the test 1 review. Most of the problems I will work out on the screen as I discuss them, except for the first 2. I have them worked out already, and I will talk about them in part because we have probably the most practice with solving linear systems at this point in the semester. So let me just talk about the steps that I did. In number 1, okay, let me also get this spotlight. Okay, wonderful. So in number 1, my goal initially is these 2 entries underneath this, the 1, 1 position, which is already a 1, I want to make 0. So I can transform to reduced row echelon form, minus row 1 plus row 2, and minus 3 row 1 plus row 3. And the result is this, okay. And then I'm good. I have zeros underneath this first 1. I'd like to make this minus 2 a 1. This will be my second leading 1. Okay, so I just multiply row 2 by -1/2. Okay. And then finally, well, the goal would be to get a 0 here and then work back up to get into reduced row echelon form. However, when I go to get a 0, okay, I take 4 row 2, add it to row 3. What happens? I get this row of zeros followed by a 6 in the vector part, okay? And this is problematic. Whenever we see a row of zeros, the dots, something non-zero, immediately we know the system is inconsistent because, in effect, the last line, as it reads right now, says 0 equals 6, which is, of course, not true. So you see, while this augmented matrix is not in reduced row echelon form, you also don't need to go all the way down to reduced row echelon form. We are row echelon form, but you don't need to keep going because we know already we will have no solutions. It'll be an inconsistent system. Okay, so this is the first one. Now let's move on to the second one. And then I will start writing on the iPad as we do problems 3 and on. The second one, okay, well, we have another linear system. We see immediately, though, we have 4 unknowns, and we only have 2 equations. So we're either going to get no solution or infinitely many because of just the number of equations is less than the number of unknowns. So I wrote this down initially where I put the second row as the first row and the first row is the second row. I could have written it down exactly as I see in the system and then interchange the 2 rows, but this is also fine, namely because I wanted to have a 1 right here. And so I just wrote the second row first and then the first. And then I want to get this to a 0. So I just take -2 row 1, add it to row 2, and here is what I get. Now, this is the next non-zero entry, or the first non-zero entry in this row, I should say. So I want to make this a 1. I multiply row 2 by -1/3, and I get this. And then I only have one more step here to get this matrix in reduced row echelon form, and that is to make this 1 here a 0. So minus row 2, add it to row 1. And then we see leading 1, and then zeros everywhere else in those columns. So this matrix here is in reduced row echelon form. Now, we have 2 free variables. You see them here. I wrote them in light green and highlighted it, z and w, right? I'm using the same. This is x, y, z, w, x, y, z, w, so z, w. These are free. And then I just write down, this first line says x plus 1/3 w is 1. The second line, it says y plus z minus 1/3 w is -2. And then I solve for x and y. And these are written in terms of z and w. And then in vector form, this is my final answer. I could have called ZT and WR or something like this, but they're already letters. So anyways, This is my final answer. This is all solutions, and we have infinitely many of them. So I have space here just for 3A, and then I'll move to the next page, where we can do the rest of 3. But okay, don't make this harder than it is. Find a rank 1 matrix with A times minus 1, 2 is this vector 3, 5, 7. Well, first of all, let's think about the size that A must be. I'll zoom in. Okay, this is 3 by 1. 3 rows, 1 column. Okay, this is 2 rows, 1 column. So what size must A be? Well, it's going to have to be a 2, and then it's going to have to be a 3. Okay, because then we have these two will match, and when we multiply A times this vector, we will get 3 by 1, which is the result that we see. So what we need is 3 rows, 2 columns. Okay, that looks good. So now let's start this. We want 3 rows and 2 columns such that A times minus 1, 2 is that vector, and we need A to be rank 1. 3 rows, 2 columns would be something like this. Now, there are multiple things you can do. You could make the columns the same. You could make the columns one a multiple of another, right? And that would both give you rank 1. The easiest way to make a rank 1 matrix, in my opinion, is just make a column of zeros. Okay, now, as long as I put something non-zero in the first column, I'm going to be rank 1. But now, if you think about what does matrix multiplication do? So I'm filling this out by columns, which means I want to think about A times a vector as a linear combination of columns. So whatever is happening here, this matrix times 1, 2 will be, if I just for the moment, and I'm going to erase, put x1, x2, x3. Then when I multiply by minus 1, 2, look at what happens. Linear combination of columns, it's minus 1, x1, x2, x3, plus 2, 0, 0, 0. Right? This is the way we think about matrix times a vector when it's linear combination of columns. And we can see already, in fact, it's kind of easy to see what the values need to be. If we look here, if we want this to equal this, I can just take x1, x2, x3 to be negative 3, negative 5, negative 7, like this. And that's what I'm going to do. So now let me erase my thought process, which is all here. And then this is negative 3, negative 5, negative 7. And then, well, this is our answer. You can definitely check, although we discussed why this works just moments ago. Okay. Now this is 3B and C. I have moved on to the next page, which is why I split the problem like that. Okay, great. We are told some information. I'm now on B. And then we need to figure out the number of solutions to AX equals 0. So let's think about this. AX, I should say, equals 3, 5, 7. Okay, inconsistent. What does this mean? Let me think about this some here. What this means, we put A, we put 3, 5, 7. Okay, then we reduce row operations to reduced row echelon form, or maybe just row echelon form. I'll just go ahead and write reduced because it's fine to think that way. And now what do we have? Well, it's no longer A, And I don't know what's happening over here, but this is going to be some. I don't know anything about here. This could be anything, really. And similarly here, this could be anything, no problem. But what I'm guaranteed, if it's inconsistent, this is going to be a row of zeros, and then this is going to be, say, C, where C is not equal to 0. Right? That's what it means to be inconsistent. Okay, so what does this mean? It means that the rank of A is going to be less than or equal to 2. Because, well, what's left? Up here, this green, which I'm not sure what is, has only 2 rows. So, and there's no leading ones in the bottom row. So the most the rank can be is 2. We also have 3 columns. So therefore, there is at least one free variable, because A is 3 by 3 with rank less than or equal to 2. If you have at least one free variable, you can then conclude AX equals 0 will have infinitely many solutions. Okay, very nice. This was B. Okay, now C. These problems I'm doing now, I think they were in 1.3. They're really good for thinking, making you think about rank and understanding kind of things that happen. We have a 4 by 3 matrix, has rank 3. What's the reduced row echelon form? So we have 4 rows, 3 columns, and we have rank 3. Well, there's only one option here for the reduced row echelon form. We have to have like this. And then here. This is the only option. One feature of reduced row echelon form is if there's a row of zeros, it must be at the very bottom. That's because every time you have a leading 1, every row above it must have a leading 1 and to the left. So there's no way that you could have, for instance, this row of zeros could not be above somewhere, because that would fail. I think that was the third property. So if you're a 4 by 3, rank 3, this is the only option for the reduced row echelon form. Here's number 4. We're given a transformation. T of x1, x2, x3, x4 is, well, you can read, but this is a linear transformation. In fact, I can prove that by finding the matrix, but we're just told find the matrix. So you can assume it's going to be a linear transformation. If instead it asks, is it, then you'd have to think. Okay, well, this goes from R4 to R3, 4 columns and 3 rows. In fact, the way you can know that, I was just trying to remember, but that's probably not the best way. What we know about the matrix for the transformation is as follows. Maybe I don't need quite as big of a bracket. So the matrix for linear transformation, we're starting off in R4. So this will be T of E1, T of E2, T of E3, and T of E4. And this is really how you see it has 4 columns, because this is generally, how do we find the matrix for a transformation? If you start off, let's say, with domain R N, then you're going to have, or say Rm, you're going to have M columns, because it'll be T of E1, T of E2, T of E3, like this. This is the matrix for a transformation. So all I have to do is just see what happens to the standard vectors under this transformation. Okay, well, maybe I'll do that underneath. Make sure we can still read the problem. Very nice. T of E1 Okay, well, this is the vector that has, okay, this is pretty easy to see, 2, 1, 4. Because this has a 1 in the first coordinate, zeros everywhere else. Okay, now let's keep going. T of E2. Well, you notice in the formula there's no x2 appearing, so T of E2 is just the 0, all zeros. And finally, well, we have 2 more, don't we? T of E3. Okay. This is -2, 1, -1. And finally, T of E4, this has a 1 in the fourth component, zeros everywhere else. It's going to be 2, -1, and 1. So now we see our matrix. This is part A. This is the matrix for the transformation. Okay. Well, part B, the rank, we could do this, in fact, very quickly, but maybe I will take 2 moments to say some things. What happens when I start performing elementary row operations? Well, let me see if I can make this actually a little smaller. Okay. It's not going to take very long to figure this out. The first thing I can do, I'll just interchange row 2 and row 1 because there's a few ways you can start. But you notice that row 1 already has the 1s there. I could as equally just multiply through by row 1 by a half as my first step. That would have been okay too. Would have been the same number of steps. So I have 1, 0, 1, -1. Okay, then I'm going to take 2 row. Now I'm going to have 2 things that I do. I'm going to take -2 row 1, add it to row 2. I'm going to take -4 row 1, add it to row 3. Okie doke. Okay, so this is 0, 0, -4, and +4. And then this one is 0, 0. Okay. Oh my goodness. Can you see already what the rank is? Do I need to show one more step? Maybe I'll make this all a little bit smaller and show one more step because hopefully, look. What do we see? We see row 3 is now a multiple of row 2. So we should be expecting that the rank is only 2. But I'm going to do one more step to convince us of that. Normally, if I was going to go all the way to reduced row echelon form, I would be multiplying row 2 by -1/4 at this moment. What I'm going to do, though, because I want to be done with this last step, is I'm just going to take, let's see, I'm going to take -5/4 row 2, add it to row 3. Yes, that's the right multiple. And then what happens? Copy. Okay, just enough space. We get 0, 0. And I'm going to stop here because just to determine the rank, you don't have to go all the way down to reduced row echelon form. And I'm not trying to solve a linear system, for example, but you see now we see the rank immediately. The rank is 2. If you wanted to go to reduced row echelon form, I'd have to just, let's see, make this a 1 and then make this above a 0, but I don't have to do that to figure out the rank. So I know the answer here. The rank is 2. Okay, so this is the end of number 4. Now we will move to number 5. Okay, we need to find the matrix. Well, we have to find 2 different matrices. We have an A and a B. First, we want to project onto the line spanned by this W1, and then we want to reflect about the line spanned by the W2. Okay, wonderful. So we could have a few choices here. We can either, for A, the matrix of projection is 1 over W1 squared plus W2 squared. And then this was W1 squared, W1, W2, W1, W2, and W2 squared. This is projection when you use any vector, as long as it's non-zero, and you want to project on the line, that is, and this meant all multiples of that vector. This is one option. Another option is to make the vector unit. This is not a unit vector. We would take this vector, divide by its length, and if you're working with a unit vector, that is along the line, then you can leave off this, or in effect, this is 1 when you have a unit vector, so you have really 2 choices. Maybe I will just work with this vector directly because this formula is not too bad, and this is all I'm doing with it. If I were doing more, which we are going to come back to this a lot in chapter 5, then I would definitely make that vector unit because I would have more things to do with it. But for now, I'm just gonna use this formula, and I'm gonna use the vector W1 as it's handed to me. Okay, very nice. So what is this in this case? This is, well, it's 1 over 1 plus 4, and then I'll try to make my straight lines. W1 squared, W1, W2, W1, W2, and W2 squared. And then if you just pull this inside, let's see, I didn't need to make that so far apart. Oh, well, I guess that's okay. If I just pull this 1/5 inside, then my final matrix looks like this. It's just a 1/5 times each coefficient. So this will be 1/5, 2/5, 2/5, and 4/5. So this is the answer to part A. This is the matrix of orthogonal projection onto this line. Okay, now B. There's also, or similarly, a few ways that you can do B. If I'm not projecting onto the line first and finding that matrix, the way, oh, I didn't mean to make that in the middle. The way I would remember it, so the formula for reflection of some vector x, it's 2 times the projection, or this is one way to write it. It's 2 times the projection onto that line minus the vector. Okay, and we also discussed that to find the matrix, so the matrix has the form A, B, B minus A, where, let's say T of E1 is this vector AB. So of course you could find T of E1, find T of E2, put those in the columns because that's by definition this matrix for the transformation. But we can use, in fact, I did in part A, I used what I know that the matrix looks like for reflection. So this is here, this is what I want to do. So all I need to do is figure out T of E1, and then I will have my matrix A. Okay, this is my strategy. But now I have a new vector, right? Maybe I need to move this down. You can see everything. It looks good. So the reflection, this is in B on the line of E1. It's going to be 2 times, well, okay, this is not unit, it's fine. So this coefficient is multiplied by W2. And then maybe I'll write out the formula and then we'll compute it. And then minus E1. And the coefficient is E1 dot W2 over W2 dot W2. This was the formula for our projection. Well, 2 times the projection. And then we subtract off the vector. Okay, so let's do this here. We get 2. And the W2 is 3 minus 4. Oops. This is 3 minus 4. And then minus E1 is just 1, 0. Okay. And then we also have this divided by. Okay, so now let's look. Okay, we can see everything good. Well, when I take E1 dot W2, I just get 3 times 1. So in the numerator here, I have 3. And then W2 dot W2, I get a 9. Maybe I'll write that here. I get 9 plus 16. That's 25. Okay, so now maybe I will do this in 2 more steps. We get, this is 6 over 25. Oh, let's just make this first vector. I think that would be a nice way to go about it. I'll zoom in for this part. Okay, great. Okay, so here we have 9 and 2 makes 18. Oh. 18 over 25. And then the second component, we see it's 12 and 2 minus 24 over 25. And then we subtract off 1, 0. And, oh. We get, well, 18 minus 25 is negative 7. And then we have negative 24 over 25. Okay, so this gets us the A and the B. So now let's write down our matrix, right? We have everything we need. Maybe I will go back to blue. The matrix of reflection. Now we can still see the problem. So A, let me get this actually. Oh no, now we can't see the problem anymore, but that's okay. We have all the work we can see. Actually here. It is. Let's fill it in. Minus 7 over 25. Minus 24 over 25. That's AB. And then B minus 24 over 25 minus A, 7 over 25. My apologies. Of course, in B, the matrix is supposed to be B, not capital A. So let me just change this. This is B, and this is B. And now this matches the problem. Okay, sorry about that. Well, I don't have all that much room here, so let's do 6A, and then we'll move to the next page and do 6B and C. Here we have two vectors in, well, we have a vector in R4, and L is a line in R4, and we want to project X onto this line. And as I was saying when we worked the last one, we're going to spend a lot more time with orthogonal projection in chapter 5, but this we can in fact do now. I will, well, first of all, W is not unit, but this is okay. We can do this without. So the formula for the projection, one way to write it is as we see like this. It's the projection of this vector X. We take X dot W over W dot W and then times W. So you see it is the projection onto a line. If the line is all multiples of this vector W, well, look, I'm creating a multiple of W. And the multiple is, well, you take this original vector X dot W over W dot W. And this simplifies some if W was unit, but I will just do it this way. W is not unit, and this formula works just fine. Okay, so maybe I will go here. What is, maybe I will come down here and do the side work in another color. So what is X dot W? Okay, we can see our vectors. Well, it's 3 minus 4 plus 5 minus 3, which is 1. And then W dot W is just, you look, it's 1 plus 1 plus 1 plus 1, which is 4. Okay, great. So here we go. This projection is going to be 1 over 4. Oh, I don't need quite that much, times this vector W, which is 1 minus 1, 1 minus 1. And we can write that, well, you can just bring the fourth and the 1 over 4 inside. Let's move this over. Maybe I will. This is 1/4 minus 1/4, 1/4 minus 1/4. And now let's copy this, and we will move to the next page, copy, and we will do the rest of problem 6. So this was, just to be clear, this is A. Okay, now we're going to move here. Look, we have B, we have C. So the first thing is, let me just recopy what we have found. So we found that this, which is the projection, is here. Okay, so now let us begin part B. This is part B. This is the component of X that is orthogonal to the line. That's what this notation is. And it's X. Let me write X. Which is 3, 4, 5, 3, 3, 4, 5, 3, and then minus, let's see if I still have it saved. Oh, okay, great. Minus this projection. Okay, so let's see what we get when we take this vector difference. Let me make a little. Okay. Well, okay, this is fractions, but it's okay. 12 over 4, this is going to be 11 over 4. And then this is going to be 17 over 4. And then this is going to be 19 over 4. And the last one is 13 over 4. Okay. Now, so let me do this. This should be, at least if we number one, did the problem right, and number two, if we understand the theory, this should be perpendicular to the whole line, and in particular, perpendicular to W. Okay, so let's do that now. That's what part C is asking us about. So part C here. What we want, verify, we want to take this dot W. And I need to be able to see them all. Maybe I'll just move this down. Okay, here we go. This is, if I take the dot product of these two vectors, you see I get 11 over 4. I get minus 17 over 4 plus I get 19 over 4 minus 13 over 4. Okay, so altogether, how many pluses do I have? 19 and 10, 30 over 4. And then how many minuses do I have? 17 and 13. Ah, okay, this is going to work. 30 over 4. In fact, 0. And so this shows that this component of x that's perpendicular, or yeah, okay, orthogonal to the line or perpendicular to the line that we found in B is in fact perpendicular to W, which is it should be. That's what we created. Okay, this is great. So we have completed number 6. Now number 7. Find all matrices that commute with this particular one. Okay, we had several like this in the homework, but this is a good exercise. And so let's do this one now. Commuting means the following. So what we want, maybe I'll write over here, we want, let me label some things. If this is capital A and this is capital B, two matrices commute. What it means is that AB equals BA. Okay. Well, this only happens when the matrices are square and of the same size. It's the only possible way it can happen, and we see that here. So that's going to allow us to solve for A, B, C, and D. So what I'm going to do is multiply in each direction and then set them equal. We know two matrices are equal provided, well, their corresponding IJ entries are all equal. So I'm going to have 4 equations that come out of this, but the first thing I'm going to do, oh, I don't want to be in red. The first thing I'm going to do is just multiply in each direction. And then I have 1, 2, 0, minus 1. After I made this problem for the review, I realized I think 1, 2, 0, 1, that matrix is one that's in the homework. But we wound up getting a different answer here. It's a different matrix. Okay, here we go. So when I multiply, oh, maybe I need a little more space. I'll just multiply and then I'll figure it out. I get A. I get 2A minus B. I get C, and then I get 2C minus D. This is multiplying in this direction, and now maybe I can just copy and paste. Let's take this one, put it here. Oh, great. And then take this one, copy, put it here. Okay. Equals. Now let's do the matrix multiplication in this direction, and then I will set the two results equal. So in this direction, I get A plus 2C. I get B plus 2D. And then for the bottom second row, I get minus C, and I get minus D. Okay, looks good so far. Now let me zoom in some because we can, as long as we can see what we're working on, and we can. Okay, so as I was saying, for this matrix to be equal to this matrix, we must have this is equal to this. We must have this is equal to this. Similarly, this one is this one, and this one is this one, like this. Okay, so what are the four equations that we get? Maybe I'll do it in a different color. We get that A equals A plus 2C. We get that C is negative C. We get that 2A minus B is B plus 2D. And we get that 2C minus D is minus D. Right? Okay. Now, immediately, we can conclude, well, three of the equations are saying the exact same thing. Maybe I'll underline them in green. This equation, and this equation all say the exact same thing. And moreover, that A and D can be anything. So far, C is 0. And then, for instance, here, A can be anything and D can be anything. Okay, so the only thing left to do is figure out what B must be, because A and D, from the three equations we have, can be any real numbers. So let's move to this third equation here, this one, and I need to figure out what B must be. Okay, so what I'm going to do is just solve for B. Okay, so I'm going to bring everything with B on one side. I'll do it here, 2B, and everything without the B I move to the other side, which will be 2A minus 2D. 2A minus 2D. And now divide everything by 2. I get B is A minus D. Okay. So now we know what this matrix must look like. So the answer here, I'll do it in gray. Okay. The answer is, well, what did I say? A and D can be anything. A and D can be anything. Z is 0, and then B is A minus D. Here. Okay, number 7. That was fun. Now for number 8. So I moved to the next page because I really didn't have enough space for this problem on the page I was on. Okay, great. Now, in order to answer a lot of these questions, we have to think about the sizes. So let me do that. I'll zoom in, and we're going to do that first. Okay, A is 2 rows by 3 columns. B is 2 rows by 2 columns. C is 3 rows. Oh, let me make that nicer to read. 3 rows by 3 columns, and D is 2 rows by 2 columns. Okay, so what can we do? Let's look at A and figure out what of these operations we can do. A is B plus D. That's okay, we can do that. They're both the same size. You can add 2 matrices, provided they're the same size. We can add B plus D, and then we multiply. So we're going to be able to do this. Why? So let me write underneath. Oh, well, maybe I'll just zoom in here. B plus D, once we add this, will be 2 by 2. A is 2 by 3. And you see these 2 match, so we can make this product. Let's do the same over here, just thinking about size. D is 2 by 2. You can certainly take D squared. It will be 2 by 2. So this will be 2 by 2. C is 3 by 3. Multiply C by a constant, it will still be 3 by 3. So this will be 3 by 3. Now, you cannot subtract or add matrices that one is a 2 by 2 and one is a 3 by 3. You can't. They have to be the same size. So this one, maybe I will start with that observation. Okay, I'm sorry if I'm making you dizzy. I'm trying to get the right view. Okay, let's start with the observation that this one, d squared minus 3c, not defined. But the other one is b plus d times a, like this. This will be 2 by 3. Okay, so first let's do this. I need to see my matrices though. Okay, let's b plus d. Oh, let's see, maybe I'm going to have to x that and then write like this. Let us write, so I'm going to have a 2 by 2. And then I'm going to have a 2 by 3. I'll go ahead and copy A. A is 1, 3, minus 1, 0, 1, 2. And when I add B plus D, well, I get 2, 2, 0, 3. Now I need to multiply. And this will be, as I said, 2 by 3. Okay, well, let's think about this. We get 2. We have 6 plus 2. And we have minus 2 plus 4. And then we have 3. Then we have 9. And then we have minus 3. Okay. Okay, great. So now we have done part A. Now part B, we're not having to compute anything. We just have to think about all possible products which are defined. And we have to think about the order of them too, because just because you can multiply two matrices in one direction doesn't mean you can multiply in the other direction. For example, okay, so what's the first one that we see that is defined? BA is defined, but A times B is not. In fact, that is part of C, although I'll get there when I get there, because if you look at the dimensions, A times B, we have 2 by 3, 2 by 2, the middle ones don't match. But we do have AC is defined. This is fine, the middle ones will match, but CA is not, for example. Okay, and then what else? Well, DB is defined. BD is defined. BA was defined. That means DA also, they're the same size, but not AD. So am I missing anything here? Ah, yes, okay, I'm missing. Here's the only thing I'm missing. The squareds. Okay, good. So we have also, we can do B squared. We can do C squared, and we can do D squared. That would be taking B times B, and C times C, and D times D. So I was missing multiplying a matrix to itself. Now, you cannot make A squared, for example, because it's not squared. You can't multiply A times A. It doesn't work out like that. So these are the ones that are defined. Well, I already mentioned, in fact, we already know AB not defined. Okay, the sizes don't work out. So now what we need to do is just compute A, which I've already written, so I will copy this. AC. Here's A. And then C. 3 by 3. Okay. Here we have A times C, at least written. Let's make sure I copied everything right. Okay, good. And then if you think about sizes here, as I've been doing this whole problem, A has 2 rows. Uh-oh, sorry about that. 2 rows, 3 columns, 3 rows, 3 columns. This will have 2 rows and 3 columns. So let's do this here. So here I have written A times C, but let's talk about it because I didn't show the steps in the video. So what did I do? I took this row, dotted this first entry, row dot column, second entry, row dot column, third entry, right? This is how we multiply 2 matrices. And then I move down this row dot column is the 5, row dot column minus 3, row dot column positive 7. And this is how we compute the matrix product. And so here is the final answer in C. Oh, maybe I don't need that, is this matrix here. Okay, A times C, and then as we discussed, AB is not defined. Now, let's see what I have left. Oh, so we have 9. We have to find the inverse of 2 matrices. And then we have the true-false questions. Let me maybe reduce the size here. And we will move on to number 9. Give myself a little more space. Let's go over 9A this way as well, in part because so much of, well, just like number 1 and 2, the operations in finding an inverse matrix involve elementary row operations. And so I have them written out and we will discuss. However, well, how do we find the inverse of a matrix? Okay, this is what's new. Well, it must be square, okay? This is 3 by 3. Then we form what you see here. This is an augmented matrix where we put the matrix A, and then on the right, we put the n by n identity. So this will be n by 2n. In this case, it's 3 by 6, okay? Then you row reduce with everything that we practiced in 1, 1, 1, 2, 1, 3, like this, the row operations to transform this n by 2n matrix into reduced row echelon form. And this is what you see here. When you do this, well, if the matrix is invertible, namely A inverse exists, then your reduced row echelon form will have on the left an n by n identity, and on the right, this will be the inverse, okay? And here, if you read this, if it does not exist, explain the reason. Well, one reason you could give, let's say it didn't exist, here it does. You'll know through this process. So if I reduce this n by 2n augmented matrix, and in reduced row echelon form here on the left, it is not the identity, n by n identity, then you know the matrix is not invertible. So if I had a row of zeros here or something like this, yeah, well, that would be the problem. If you don't get the identity on the left when you do this, your matrix is not invertible. So let's talk about these steps. Okay, this kind of thing we have done many times, right? But doing it to find an inverse matrix is what's new. I want to put zeros underneath this first leading 1. I take minus 2 row 1, add it to row 2, 2 row 1, add it to row 3, and ta-da! Here is what we get. That this is the result right here. Then I already see my second leading 1 will be in the 2, 2 position. I take minus row 2, or minus 1 times row 2, and here it is. And then I would like to make this entry a 0, so I just take negative row 2, add it to row 3. Ta-da! Again! Now, if you look at this matrix, you will realize we are in row echelon form because here, right? But row echelon form really doesn't do anything for us when we're looking for A inverse because we're not finished. So what I need to do, in fact, this leading one's okay. I only have zeros in this column, but this entry here and this entry here, I need them to be 0 to be in reduced row echelon form, and I can do that in one step. 2 row 3 added to row 1. Row 3 added to row 2. And now we are in the final step. We see the identity, and that means this 3 by 3 matrix here, as you see, this is the inverse of A. Let me label this A, and now I'll move on and do B right here. There's not a lot of space on the page, but I have room for B. Okay, this is a 2 by 2 matrix. Here, A 2, 3, C. And this is something we discussed, that I mentioned the word determinant. And for a general matrix, you don't have to worry about what a determinant is yet, because that's coming later in the semester. But for 2 by 2s, the determinant of this is, well, let me get my laser. It's this minus this. So this gives us a characterization of exactly when 2 by 2 matrices are invertible. So let's write that here. What I need for this to be invertible, because it says find values A and C, we can just find one set, one A, one C, that work together such that this little 2 by 2 matrix is invertible, and then we'll find A inverse for our specific choice. Okay, so what we need is that AC minus 2 times 3 is not equal to 0. So you have a lot of freedom with your choice of A and C. Just don't make them multiply to 6 and you're good. But I'm going to pick, what's the easiest we could pick? Well, either both 1 or both 0, right? Because that would make the matrix pretty easy. So let's make them both 0. So I'm going to choose A is C is 0. Okay, so here's part of the problem right here. But like I said, any two numbers, as long as their product is not 6, will work, and the matrix will be invertible. Now, let's write this matrix, and I will recall or mention the formula for an inverse of a 2 by 2 matrix. So what I need to do is fill it in with my choice. I chose 0. 0, 0. And then the formula for the inverse is, okay, well, you take 1 over the determinant, which is this, okay? So we take 1 over, in this case, it's minus 6. And then you flip the diagonal, or you interchange, maybe that's a better thing. You interchange these two. Well, I interchange 2 zeros and they are 2 zeros. And then you take negative of the off diagonal. So this will be -2, -3. And this simplifies some, right? In fact, I will make it simpler. We will have, when I multiply, I will have 0, 0. This is a third, and this is 1/2. And if you'd like, maybe I will, because I have space. So first of all, let me box my answer here. But then let me draw a little box over here. You can check. We should get that A times this matrix is the identity. And similarly, this matrix times A is the identity. But you know, whenever you have an n by n matrix and you have another n by n matrix, you only have to check one side. So you get the product of the two is the identity, and then automatically that matrix is the inverse. And if you multiplied the other way, you would also get the identity. And this is really, is important to understand. It only holds for square matrices. Okay, so let's just check. And then we will move into multiple choice. If I take, what's my matrix? 0, 2, 3, 0. So now I'm doing A times A inverse, although I could have checked the other way. Oh, nope. This is why it's good I checked. 2 over 6 is not 1/6, it's 1/3. I was looking at it realizing it wasn't going to multiply right. And then I realized I had written it wrong. 2 over 6, 1/3. Okay, hope we're okay. Now, this is why, well, you've probably seen me make mistakes before. I try to edit them out of videos, but if you were actually in person in class with me, you would see more mistakes than you've seen in videos. So I would just say, I am human just as you are. It's why it's really good to check your work when you're taking an exam, because mistakes happen to anyone, no matter how much you studied or how ready you are or any of that. Mistakes, they just happen. Okay, so now if we multiply these two, you see, in fact, we get 1 here, we get 0 here, we get 0 here, and we get, oh, goodness, and we get 1 here. So we do have the identity, and this is the correct inverse. Okay, now we move to multiple choice. I just flashed the answers, true, false, whatever. But I want to talk about why, because that's what really matters here. So I'm going to go through, I think there were 12 true, false. I'll put 4 per page, and we will discuss. Okay, so here we go. This page will be A through D. Maybe I will use different colors. Well, A, of course, to answer true here, all I need to do is construct one. So 5 by 6. So why would there be, well, the rank 4, it's certainly less than the number of rows. It's less than the number of columns you can create. And so I need here to make one to fully justify. I need 5 rows and 6 columns. And I need rank 4. So I might as well just fill it in only with zeros and ones. There's rank 4, and now I can just add 2 columns of all zeros. There we go. There is a 5 by 6 matrix of rank 4. Very nice. Now, what about B? Well, the answer isn't false because we know the rank of A. Let's say A is n by m. Then the rank of A must be less than or equal to n, and the rank of A must be less than or equal to m, because, well, the rank is defined to be the number of leading ones in the reduced row echelon form of A. We are moving on to C. This is definitely not the case. In fact, I can find some 2 by 2s that fail. Here's a 2 by 2. What's the rank of this? It's 1. Here's a 2 by 2. And what's the rank of this? It's 1, right? Good. The first one's already in reduced row echelon form. The second matrix I wrote, to get it to reduced row echelon form, just multiply through by -1. But these two sum to 0 matrix. And here, the rank is 1. The rank is 1. And we add them up and we get something of rank 0, which is not 1 plus 1. Okay, so this is why C is false. And in fact, D, we can use as false from the exact same, or at least part of the exact same example. D is false because this matrix here of all zeros, this is in reduced row echelon form. In fact, I had a question in Teams. Somebody asked me that. Is the matrix of all zeros reduced row echelon form? Absolutely it is. It's rank 0. In fact, this is the only rank 0 matrix, is the 0 matrix. Okay, we have no leading ones. The rank is 0. So we see this matrix is in reduced row echelon form. At least one of the entries in each column must be 1. Well, that's false because the entries are all 0 here. Okay, so here what do we see? This is letter E. If it says it's true, well, let's discuss why. We have a unique solution. This means there are no free variables. If you have no free variables, well, then the rank is the number of columns. It's a 4 by 4 matrix, and then in particular, just this part, having no free variables, ax equals 0, will have only the solution x equals 0. Okay, this is true. Okay, looks good. Well, in particular, it's good to observe that ax equals 0 is never inconsistent. This one, this is a comment that we will come back to more when we talk about the kernel and things. This system that I have circled many, many times, no matter what your matrix is, even if we didn't have these hypotheses, it's never inconsistent because a times 0, the 0 vector, is always 0. So this system always has at least one solution. But given that we have no free variables, that comes from this part, we know that's the only solution. Okay, very nice. Now, let's think about F. This is definitely false. Let's just come up with an example. So now I am on F. Now let's discuss number F. Well, this is definitely false, and I just have put here, this would be 4 by 3. Maybe I'll write that underneath just to think about the sizes. This is 4 by 3. This vector is 3 by 1. The result will be 4 by 1. But we have a lot of choice here. We can pick A and we can pick X. We just need there to be a solution. If you think about matrix times vector as a linear combination of columns, it's very easy to construct something that works here. So what can I do? I can just put and then literally anything except this last column needs to be this. And then I can put anything in my first 2 columns. It really doesn't matter. So let's just do it. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then linear combination of columns, you have 0 times the first column, 0 times the second column, 1 times the third column. This is exactly this vector. So, you know, in fact, you could come up with many more examples, but this is definitely not inconsistent for all 4 by 3 matrices X, because I found one 4 by 3 and I found one X, for example. Okay, we could have come up with a lot of other examples on this one, but I just needed one. Okay, now let's do G and H. G is definitely true. Why would this be? Well, it might seem weird to just say, well, it just looks linear. You notice 0 goes to 0, and then I only see things that have power 1 in them. But if you wanted to prove it further than that, so I put a video of one of the homeworks where I justified why something was a linear transformation. You have 2 different ways you could. One, you find the matrix and verify that that is what's happening, that T of, in this case, would be XY, is the matrix times XY. That's the definition, or there are 2 properties you can check. Maybe here, just as an exercise, let's just show the matrix for this transformation because this is part of the topics for this exam. Anyways, to get the matrix, I know the matrix would be T of E1 and T of E2. So let's calculate those here. For this transformation, T of E1 is 1 minus 1, and T of E2 is minus 1, 1. And so this says the matrix of this transformation better be 1 minus 1 minus 1, 1. And you can just check A times XY will be, oh, maybe I should leave a little bit of space here. Well, it's X minus Y, and it's minus X plus Y, which is exactly that, well, it's exactly that operation, right? Okay, now let's do H, and then we have 4 more that I'll put on the last page. This is definitely false. The easiest way to see that this is not a linear transformation is this map on the 0 vector gives us, well, look at the map, 0, 1, which is not equal to 0. And any linear transformation must satisfy that 0 maps to 0. Okay? And this one does not, so it's not a linear transformation. Here are the last 4. First of all, I, false. Well, what is a matrix that represents rotation? A matrix that represents rotation is of the following form. It is, maybe I'll do this. It is cosine theta, sine theta, minus sine theta, and cosine theta. And this is the matrix for rotation. Theta, maybe by theta, counterclockwise. Okay, now we do see a number minus the number, a number, except if the cosine of theta is a half, the sine is definitely not a half. So, well, how could you argue that? We need cosine squared plus sine squared is 1, and you notice that 1/2 squared plus 1/2 squared is a half, which is not equal to 1, and so 1/2 1/2 is not equal to cosine theta, sine theta for any angle theta. But you could also just say, well, you know, if the cosine is a half, the sine has to be square root of 3/2. So this is not rotation by any angle. Okay, and the last 3 are all true, and the last 3 all have to do with invertible matrices and inverses, and this is our newest topic for the exam. If A is invertible, A commutes with A inverse. Absolutely it does. We've talked about commuting with a matrix even in this review, but we know A inverse is A inverse A, which is the identity. Okay, so that says exactly that A commutes with A inverse. K is true, and why is this? Well, let's start with the left-hand side. We'll prove it. The left-hand side, A squared inverse. Well, we have formula. Well, first of all, we know A squared is A times A. And then this is, now let's remind ourselves the formula underneath. There's another way I could argue this, that K is true, but we know if you have AB inverse, this equals B inverse A inverse. It's a property about inverses, assuming A and B are both invertible, and they're both the same size, so that A times B is defined. So if they're both invertible n by n matrices, then this is a property. Well, if I apply that here, it just says A inverse, and this is A inverse squared. This is one way to prove that formula. This one's interesting. L is also true. Okay, so A is invertible. This is an important part because if A is not invertible, this last line would be false. A is invertible, and we know A squared is A. Why does it follow that A must be the identity? Well, what did I do? Okay, there we go. That's what I meant to do. That's A squared. Just 2 of them, not 3 of them. With 3 of them, that would not be the case. A squared is A. Okay, now. So we need to conclude that A is the identity. Well, A is invertible. So I can just multiply A inverse, and then I have AA. And this will equal A inverse, and then I have A. And now we can do a little bit of simplification. You see, matrix multiplication is associative, which means I can, let's use this, I can multiply these 2 first, right? Because first I was taking A inverse times A squared, but I can multiply these 2 first, and that's fine. And those 2 multiplied, A inverse A is the identity. And similarly, this is the identity. And so what follows from this, we get that A, okay, now we're okay. We get that A is the identity. Over here, technically, it's the identity times A, but the identity times any matrix is the identity. Okay, so that's the justification for the last one. And this concludes our test review. Hooray! Okay, well, good luck studying.